Hello, everyone. I'm Mike Hines, Executive Director of the Fiber Optic Sensing Association. Welcome to today's webinar. We're excited to have Dr. David Chen of Foton joining us from Princeton, New Jersey, to share his thoughts on the application of fiber optic sensing as part of a telecom and datacom architecture. David comes to us with decades of experience in photonics research, development, and commercialization. And today he'll focus in three key areas: optical pulse duality, Foton's echo controller technology, and he'll detail a DAS, polarization OTDR, optical power meter triplet setup, which is essentially how the architecture for his system is described. David holds many US patents in the hundreds. He earned a BS at Shanghai Science and Technology University and continued in academia, earning 2 master's degrees and a doctorate in theoretical physics from the University of Texas at Dallas. So in 2018, David joined Foton as the CTO after a distinguished 23-year career with Verizon. So David, with that said, welcome, and we'll turn the webinar over to you.
Oh, Mike, thank you so much. You can hear me, right?
Yep.
Yeah, thank you so much. First, I just want to thank you, represent the Foton, for this opportunity to present our invention, and also I'd like to thank Joy for your advice and coaching. Okay, let me start for the presentation. This is the topic, as Mike said. It's a full duality for DAS, P-OTDR, and OPM. And this is the target. Its goal is to really try to leverage the AI for optical networks, for integrating the cloud on the ground, which I will explain, and edge cloud and OSP plane for the sensing application. And here is our basic agenda. First, we have to say is without the hardware control, just talk about the DAS itself, it's not very much useful, because you have to use the hardware to control and then the software entangle. And so this is what we have invented for quite a few years now. This is our controller. We will explain to you for what is the echo. Then we go to the full duality of DAS. P-OTDR is polarization or OTDR. OPM is a power meter. And with the highlight of how this works, the basic principle, and then the true triplet setup for the cost reduction, and for the future inter-data center CO and mixed nodes. And of course, Mike always wanted me to say this, and he asked me the questions: full duality, is this absolutely necessary? Yes or no? Yes, if you want to implement that, but no, if you want to choose the standalone, so we call self-conjugation unit, we can do this as well. And then, of course, the node-to-node synchronization, we're using the echoes controller, we can make it our timestamp much accurate than the traditional network time protocol. And the basic product development requirement, which we have to meet the requirement, not only just by the imagination and the physics. And of course, then leads to the future we're all fighting for together. This is this industry, for the industry civilization, is the AI and how this cloud on the ground architecture will work. So let's start with what is Foton's Echo. This is a new platform for optical network sensing controller. Like I said, with this controller, we can manage many sensing equipment. But the Echo itself is an interface which bridged the user community, the computer community, the WDM community, and also communication community into an architecture which is visible. So let me go through a little bit, because this is the product. This is not a prototype. So what I want to do is to go find the list from here, 1 to 7. First is the co-ferro mating detection. We converted the axial engagement force into a sensor switch. So once you push it in, if you're not pushing all way in, latching on, we use the LC connectors, latching on, you definitely will not have activated the switch, which will tell you it is not properly seeded. Then the next one is number two. This is a 0, we call 0 is the hardware side, and the port distribution indicator. So once you push it in on the panel, it will tell you which port is engaged and which port is not engaged. So this is the number two. And number three is really the end-to-end continuity indicator. So if from ISP to OSP, which is outdoor, we have product. From outside the plant, which is with different requirement for protections, indoor is a panel. And if end-to-end is connected, the indicator will tell you, aha, from A to Z is all connected. Then what happens is we're using our Go Photon's own design and manufacture for the PD. We have extremely low dark current and sensitivity. So we're using this is using the bidirectional. So this number 4 is the bidirection. We sensing the noise. That means we only can touch about the 1% of the power, because due to our very high quality PDs, we can do the 1%, and we can sensing that bidirection. So if you plug this in, and if sit down there for a while, and you don't know where this has a traffic or not, you cannot just go back to go see the basic record. You want to see the live. So the live tells you whether the traffic is from east to west or west to east. Then the optical power translator for what happens if you tap into, let's say we tap into 1%, and if you have let's say minus 20 dBm, and we can you have, let's say we're sensing the minus 40 dBm, which is really the below noise. We could convert it into what is exactly on the transmission line on the fiber. Beyond that, and then this will indicate, tell you, aha, this is to go or not to go, because if the fiber is too lossy and the quality is not good, and they send a signal through, and we can tell you where this is good for noise floor for the transceiver or not. Then we also expanded into the environment, which is with temperature, the vibration, which we will talk about today, is the acoustic sensing is the vibration, and the vibration on the equipment, and as such, and then also the mechanical balance, which means if the tilt of the wind blows, sometimes the flip over, we can precisely tell you how this box is performed on the pole or whatever. And all this is using the non-intrusive kind of a method. And all the data is collected to incorporate into the OSP plan, outside the plan, and then cloud on the ground. Why it's cloud on the ground? I can just make this a little clear, because if all the fiber is buried under the ground and you have beautiful record, but after a few years, you don't even know. Even after a few years, you have good record. The fiber has fiber cuts, fiber has different, we know, just a degradation, all those kind of things, and you just simply don't know. And you want to go back to redo the OTDR, everything. It's just so, basically it's impossible. It's so much time consuming and the effort and all those kind of things. So with this, you can pretty much keep everything alive, and you can see that. And can you imagine if all the record can be lifted onto the computer, which is considered as cloud on the ground. Now this is the equipment, the product. So this is the computer. We have the software versus hardware. We build a kernel. We have a PCB board, and guess what? This port pushed in, and I'm not so sure. I think Paul Dickinson came to our booth, and I tried to ask him to try it. They basically push this port in, and the light kicks on. And this is the called engagement sensor. And of course, internally, you immediately can see from this software, the display, you can see whether traffic on it or not traffic on, all this kind of thing. And this is live. I'm not going to go more detail into it. This is a picture, shows the reality, the product. Now, we need to tell you, based onto the controller, the echoes, basically port-to-port mapping, everything is engaged, is sensed, bidirectional traffic is sensed. Then we can go to the next step, is the advanced the Foton Duality development. And this is the DAS P-OTDR. Why I can say P-OTDR is because using DAS, we're using coherent, and using polarization, we take advantage of that, and using the P-OTDR, the two orthogonal signal, so we can take advantage of that, and then we can average that, and also it's very clear. And we are doing some very fancy coherent detection technology as this moment. And of course, PM, you have the power go through, and you immediately detect what's the total power, whether is it good or not, go or no go. So this is a true triplet unit. And this is really energized by the concept of engagement, entanglement, duality, conjugation, and this is a fiber for those folks that design fibers. And you definitely will understand the Cramer's rule, which is the linear system, and the real part and the imaginary part is entangled together. So whether you're using the hollow core fiber or using the solid core fiber, the performance is very differently. So we are the scientists taking the advantage for using that. So this is energized by this concept. So we need to do duality. Now we want to show you why, how this stop. I want to like to give the credit to the industry. Of course, this picture is downloaded from internet, and you can see from the top three one. The first one is a fiber to fiber, exact the same fiber. So the architecture for the fiber structure is very similar. Therefore, you get a Rayleigh backscattering, you get a loss. On the other hand, I worked with Corning, OFS, Prysmian, all those good companies developed the bending sensitive fiber. And if you do the bending sensitive fiber, even the mode field is pretty much the same, but the structure changes is changed a little bit. Therefore, when you go from east to west, west to east, if you switch the fiber, OTDR gives you artifacts. And this is intrigued by this field issue. And when I was in the Verizon, I looked many times with the field technicians, and they basically has the issue. They don't understand why, and we contact the test equipment, but this is a physics phenomenon. We cannot do anything about it. And so how can we do that? We have to do the bidirection, and we do the average. So this is the way, and we want to make sure the Rayleigh backscattering is not symmetrical, and that part we cannot do too much unless we do the bidirection. And of course, the insertion loss is symmetrical at the bidirection. And if using this OTDR trace, you see this is dead zone and then comes into a reflection, and to the end, which is a reflect. This peak is not a Rayleigh backscatter; it's just a pure reflection and an open end. And I like to thank to the folks who did a very hard work is the EDVAR, and I work with their scientists, and lucky enough, very fortunate to work with them and develop this filter and produce that filter. And I think that this is also a very good application. So all this is a pioneer work in the industry, the problems, issues, and we're going to introduce into the new invention. So this is the hits into the Rayleigh backscattering noise floor. We cannot do too much about it. So the OTDR has a limit in terms of distance. Now is the OTDR. So first they're doing the OTDR. This is the last year, not this year's demo. It's also a live demo on the floor. It's by design of OTDR A and a B. Now everybody understand that doing the OTDR using Rayleigh backscattering, and you have only a very small fraction of the power coming back. So this, if this main power goes through, 100% goes through, you get about 1% or 2% or whatever is coming back. And this is converts into fiber loss, which is the waveguide loss, dispersion, all those kind of things, plus the Rayleigh backscattering. Now, think about it. If you shoot the laser through, this whole pulse, 99% of power, 98% of power totally lost, going through for nothing. And only we extracted the Rayleigh backscattering. Is this what we really want? And I'm kind of a guy bit cheap on this. I don't want to waste anything. So by switching the back and forth, and we can do a lot of things. So we can, if we use A to B shooting, and the B side of we immediately converts into a power meter, and we detect the power. Now, let's say this fiber has about a 20 dB loss. Now, you know the record for 20 dB loss. However, suddenly you see 25 dB loss, and you don't know why. It can trigger, the alarm can do the detailed fiber trace, and which using the OTDR and using A to B, B to A. And if this is 80 kilometers, maybe it's okay, but if it's 120 kilometers fiber, then you have some bad luck. You have to use in bidirectional. So we implemented that. We trying to work onto that. That was the time was an option using optics cross connector, and which is optic switch. And the highlight is basically this can be standalone as well as the bidirectional. And this is enables the first phase of a cloud on the ground, because basically the fiber characterization, basic characterization can be exposed to the controller. And then this year, actually, Paul came to our booth, and also we had a press release, and this is a real live demo for the prototype, not a final product yet. So I explained to you. So this is the advanced the OTDR plus the DAS. Okay, this is the DAS. And DAS, of course, you know, is using the coherent interference and see the acoustic interference stretch caused on a fiber. And we're using A and B. So, but the B side, we are just not getting, not just the OTDR type and not just the OPM type. We have to use the coherent detection. And the coherent detection is really trying to see how the pulse is disturbed. And if you have a pulse going through, you have lots of loss. It's still same phenomenon physics, 90 some percent of it going through and a few percent are going back. And that going back is basically extracted the disturbance by coherence analysis. But going through, it also, the pulse itself also experienced the turbulence. The turbulence, and it's because works in the linear region, and people talk about dispersion, and it's a convolution or this kind of impulse response function for the fiber. But we can look at this as well. It's as far as in the linear region, we can look at all the accumulated the disturbance, acoustic turbulence, and going through, and we can use in different type of sampling to see how the pulse is disturbed. Of course, if you have very small disturbance, and we see it's not such a big deal. But if we see lots of disturbance, then you maybe want to check out what's going on. So you can do the A to B, B to A to shooting the lasers to see that. Of course, we have the OTDR as well. So we can see the vibration, oscillation, the acoustic, and also the fiber loss, and also the behavior. And then, of course, we did apply an optic switch because we want to protect the lasers when we switch. This is very, very honest phenomenon. You shoot the lasers through, and you have so much power. If you don't protect the receiver onto the disturbance check, you're in bad luck. So we synchronize this through the Echo platform. And you know what? We figured out this is a perfect design for all you guys who want to implement the future inter data center application. Basically, you want for the reason of a real estate issue or this any kind of issue, you want to move to another second data center for replication, maybe 30 kilometers, 20 kilometers, or 80 kilometers, even to 80 kilometers away. And this is almost a perfect application design for this design, is because you cannot just using one DAS, you need two DAS anyway, but why not just to entangle them together, okay? So next one is talk a little bit about the synchronization, because that is, we do use the concept of special relativity, and of course Einstein's invention, and Echoes is the controller for the multiple fractal geometry kind of distribution. You have A and B, just for this example, and this is the cloud. And due to the nature of the NTP may not be so accurate to a certain limit, but we can design do a fine tuning. We send it simultaneously, send it a pulse signal to 2 unit, and get the signal back at the dual response simultaneously, and doing back and forth. Eventually, we can try to zero in to the accuracy. That accuracy, it could even reach to the pulse width limitation, and whatever the pulse you use, and of course even more accurate than that. Now this is the real display. It's a prototype. It's not final product yet. It's because it's the desktop, and we don't have too many fancy widgets in there. And but what we do trying to show you is on the left is the DAS display, on the right is the turbulence display. And we have 30 kilometers of fiber. In between is a speaker. So of course, I didn't have the chance to show Paul if we take the radio or YouTube put onto it and show the Lady Gaga singing, and then after a while, and we can take that and it can replay this the sound. But just so busy, and the floor is very noisy. So this is the DAS sent through the coherent turbulence sensing, and this one is coming back to the DAS, vice versa, the two units, because the floor and the space is very limited, and this equipment is extremely sensitive, so we cannot do too much tricks on the floor, but we can do this in the field, in the lab. Basically, we need to tell everybody is what is the requirement. We just cannot just do a scientific research and tell everybody, say, oh yeah, this is the things works, and mathematically works, and physics should work. But we are more realistic. We have to see what is the requirement, and what is the benefit, and what is the predicted timeline. This is also always very important, because for us, Foton is it's a manufacturer and a product. We always look at the delivery, not just tell you, oh, we can do this physics. That's not good enough. We want to deliver, and we want to predict time. So I want to give all the credit to the industry pioneers, like Mike said, and I appreciate your advice. And I need to tell everybody, I don't know how I can explain. It's just extremely appreciated for all the pioneers. Since I worked for Verizon before for many years, 20-some years, so I give first listed a few papers which they did a fantastic job from the Verizon for the last few years. And after that is also the industry. You can find lots of vendors. Some of them exist, some do not exist anymore. But doesn't matter, because those are the credit goes into those scientists, engineers. They did beautiful work. And also FOSA website, you have lots of YouTubes, and I can list them all. But this is just for your experience, for your reference, what we have observed and what we have learned from you guys together, and we can do something different. Now, this is the design. So triplets, okay, the triplets, like I said. So triplets, I like to use a scenario. You guys may never be prepared. Say, oh, people say, oh, they'll be more expensive. All this, actually not. Okay, I can tell you this. So we are not going to talk about a price, but I'm going to talk about a strategy and a design strategy. Can you imagine if you just go to a car dealer and you spend a few hours negotiating everything, come out with a nice car, and before you step out or want to drive away, two other divisional sales people comes in, and one tells you you have two extra freebie. What a freebie? Two vehicles. One is for two drones. One is for air. One is for the water. I can guarantee you will not think about it. Just do the work all the time. You will think about next vacation. One maybe go take you to the Himalaya. Other one take you to the Bahama Beach. So you have everything. And this is one fits for three. And the DAS, OPM, and OTDR. And this is the basic function, and it's a fully duality. Requires some entanglement, requires some synchronization. Like I said, that's why I present to you about the time synchronization, so we know how to switch A and B, B and A in a timely manner. And then this is the design architecture. Then moves into the OPM, DAS, and the handset. Just do a desktop is relatively simple. So what we want to do is we want to do the handset. Handset is the desktop. So this is the requirement of dimension, basic dimension. Okay, we designed it. It's a 30-inch touch screen, and then the function characteristic is the triple DAS T. And of course, this is all these three included. And also, I work for Verizon for the industry, and I work for the standards and also safety. And we definitely want to make sure it's safe for the users. So this is the class of laser we want to focus on to it. Because that, we cannot shoot too long, because the laser is limited for the power. And if that is the case, the duality makes more sense. So we integrate it with the major acoustic, the OTDR power meter, so easily accommodated to the test. So you can take this one to some field, you plug it in. If plug it in through the ecosystem, then everything becomes automatic. And of course, the switch can be attached as well. By combining the intelligent terminal and the cloud servers, which any big company may have their own management system, we can pass the data to them and utilize the most advanced DAS with ultra high collection sensitivity. That part is our expertise, trying to do the coherent detection portion. For the sampling, there's lots of tricks you can play. And based onto the class 1M laser, that's the pulse width intensity is all determined for safety reason. The leftover is the software and the tricks. So equipped with the wide and wireless, and basically is Apple and Samsung's interface. Hopefully we can get these apps into that. And this is of course the future. We have not developed this yet, but it's in the development. And of course, portable is lightweight. So for the indoor and outdoor, all works. This is our goal. And then next one is just really thinking about the data center. Of course, this picture is copied from internet. I mean, by the way, I worked for Verizon. I built the first 5 years. I built a data center, and I know how important it is to see and coordinate with all the equipment. And so this is what we have for the vision for data center, and with the 2 unit. Of course, if you guys in the industry, not you guys, just industry require for just a stable desktop, of course, we already developed that. But also the next step is portable. Portable we can take to anywhere, and so if a data center we can put it into, and then we can use the data center, and assume is passing through the echo. Assume, but not necessary. And you guys can using your software and network management system to tie those applications together. And of course, this is OTDR. This is designed for 80 kilometers, and so the DAS is a little bit shorter, about 60 kilometers. 50 kilometers is very sensitive. 60 kilometers beyond is a little bit shabby, is because the laser and also the requirement for safety. So those are requirements that we can, the OTDRs, we designed it for 90 kilometers of the fiber loss. Does not mean the distance. Sometimes the fiber is a little bit lossy, and sometimes not. And this is what we have designed, and it works beautifully. This is displayed and coupled with the DAS. And this is the requirement. I have to respect, like I said, I used to work for Verizon, so I have to respect Verizon, the requirement. They told me this is what they want. So this is the reference to the Verizon, the ECOG paper. It determined the location, everything. So I'm going through a little bit quicker onto that. So determine the activity. So Verizon's application, their proposal. Okay, first is the monitoring the abnormal activities near the cable. And near the cable, and the second is the cable identification. Cable identification, which is okay. But with the cable identification, with the echoes, we can precisely tell you which fiber going through which cable onto the port-to-port continuity panel. So this is Verizon's dream, and the instruction and the proposal. Actually, we already fulfill that using the echo to fulfill that, but not as a final product for that. And determine the location along the cable. So this is the DAS. You choose that, and you can see the Rayleigh backscattering for the interference, and the intrusion detection for telecom fibers, of course. And this is what they want. Is the sensing for the network, which is through the wireline wireless. The next one is basically identification of each fiber. That has to do with the port. Now this is we detected it, we tested it in the lab, not in the field yet. We hope we can go to the field very quickly because there are lots of requirements on that. Lots of potential customer wants that, and so once we put this into that, and like I said, with our echoes, we can not only just do the data, the DAS, also the echo itself has the environment sensing, all those kind of things. That's just very good for. And what they said, the vegetation, a specific fiber, and they can map the port. And the duality enables the precise calculation, because one way shoots, let's say you have 2 data center, it's 40 kilometers away. And if you shoot the pulse through and you know a certain location, since the Rayleigh backscattering is not perfectly symmetrical. So can you imagine if you have a dual DAS, you shoot it back and forth a few times, and it precisely determines the location and disturbance. All right, so this is the future. I want to keep myself, now it's 29 minutes, I want to keep at 40 minutes, like Joy told me. So this is the application for pure network. Now I work for the Verizon for the NGPON. So you have the burst mode for the OLT and ONU. So when OLT, the broadcast, ONT is the burst mode to talk back. So if this is the architecture, we think about it, the dual DAS could be exactly designed this. We have multiple nodes and with multiple duality design. So in between is the network cloud, and we can take turns. When this OLT is talking, the other one can be listened. And then switch around, the rest can talk, taking turns. And this application is designed for bidirectional duality, and really works well, should work well for the interdata center applications. And the beauty is that when the electrical power is turned on, turned off, it has no impact to the customers. Because this VR sits on another layer, there's an acoustic layer, and the trace will not impact anything. Okay, so this is a question I'm not going to go through right now because I want to go through quickly. We will go back, and Mike will handle that, and to handle the questions that let's discuss a little more discussion. But I want to make sure you guys see our future development, which is pending. We are working on it, but it takes lots of effort. It takes time. First, it's just the using the fiber OTDR, for the discontinuity. And what we want to do is we right this very moment, I said a very clear a triplet. So quadruplets, quintuplets could be in the future. What does this mean? You have a piece of fiber, you send a pulse and goes through, and you have a pulse width, and you have see the dispersion broadening. And then if we put the dispersion compensator into that, because per channel basis, of course, the shoots the laser, shoot the DWDM, and you focus onto a specific pulse, and using periodic fiber grading, all this kind of thing. There's many technologies has already been very maturely developed, and we can see the pulse, and then we can compensate that, and then send it back. We can send it back, do a back and forth check, so we know exactly how the pulse is associated with the transmitter. And by this way, we can use tunable lasers. We can do not only just the dispersion, a specific wavelength, let's say 1550, we can do a dispersion slope check. And also we can possibly predict the zero dispersion and non-linearity, and not only the dispersion, but also the fiber loss, because we going through this, we know the fiber loss, we know the dispersion, we know all the impairment, and then this whole fiber is fully characterized by the basic fiber characterization. And this is something which we are working on that. And I think this is the future. We can go even possibly move into quadruplets. Okay. And then the next one is a little bit more fancy, which is a really advanced research. I'm working on that, and requires a full knowledge of the state of polarization for the PMD and doing that. Currently, the entire industry is doing the coherent detector, which is the two-dimensional pattern in terms of degree of freedom for signal. But if you can go to the polarization, and which opens up a 3D communication. But we are not going to the transmitter receiver. Rather, we can use echoes to do the controller. We send a signal, see what happens, and we lock in the timestamps. Okay, we have to synchronize. Otherwise, the PMD that changes all the time. The SOP it changes all the time, and we have to synchronize to a less than a pulse width. And if this continues on back and forth, we fully know even what the impulse response function for the fiber in terms of polarization, which not many people talk about this anymore, but this is also a fancy step to see the 3D of the interface. And if this is successful, we can predict it can even goes into maybe 1/3 or 1/2 of the pulse width. Okay, and so this is ongoing, and what I'm just trying to share with you what we are doing. And the last thing is this one, as we promised. Now the red one is planned for the future. I just have to say very clear: a 13-inch handset is not delivered, but the rest we pretty much delivered in OFC. The last one using the yellow. The prototype delivered at OFC is a working unit. And of course, these are the very basics. The basics keep us and with you, but we are very honest because of what we are doing at this moment, all the specs, I'm not gonna hide anything, it's all open. Now, detail intricacy, how we do the thing is a little bit tricky and I don't wanna talk too much, but we are going into the wavelengths, even move into 1640, 1650 nanometer, and for different the applications. Okay, so my talk just right here, I just talked about close to 40 minutes. Mike, I'll hand it back to you, and also I'll put back to the questions you coached me, and so I'm gonna ready for the Q&As, please. Thank you very much.
Right. So we actually have some questions from the audience as well, David. So thank you very much for the presentation. Let's go to the audience questions first, and I think if we can touch on some of the published questions here toward the end, we'll do that. If not, we can handle those by email later on. I think part of the question, one of the questions that was asked early in the presentation was what the scattering mechanism was, and I think you've answered that using DAS and a coherent Rayleigh is the scattering mechanism that you're basing this on. But it does raise the question, could you apply this to a Raman or Brillouin based system as well, now or in the future?
Absolutely, but this is very different, right? Because this is this moment using just the 1550 or 1620, but using, okay, this is a beautiful question, absolutely beautiful question. Let me speak in terms of a little bit physical sense. Physics, the Rayleigh backscattering is more into the linear region called elastic collision. If you move in the Brumman scattering and the phonon and the Raman scattering, which is non-elastic collision, that is the difference in terms of physics as well as in terms of the energy is scattered back. So it requires a different transmitter and receiver. Can we do that? Yes. But at this moment, I like to focus on to the acoustic, the linear region, and the elastic collision domain.
Great. So the next question has to do with the application of this to telecommunications networks. Basically, I think the essence of the question is, can you apply this to a telecom or a data center network without interfering with the network's operation?
Another wonderful question. Yes, depends on the application of the data center communication wavelengths. So by speaking that, first, we have our echoes. The echo will basically sensing the noise, and also if you need, we can basically sensing the WDM pulse, see which color of the light is inside the fiber. Then we can software, we can skip that communication signal wavelengths. We can launch a signal which is beyond that. And of course, the easy way to do that is moving the wavelengths into 1650 region, because C band and L band is terminated at 1625 region. So beyond that, and this moment is not occupied for communication, so we can use it as the DAS. Or if we just look at it up, if you have C-band populated onto the fiber, and we can go for the S-band or maybe O-band and the E-band type. So this requires a tunable laser, and of course, theoretical is durable. It's all this end up with a cost, right? But in terms of physics and the design, the answer is yes, we can do that. We can do that without interrupt the communication signal.
Great. Okay, thank you for that. Another question is it has to do with commercialization. Has GoPhoton developed the DAS triplet setup sort of integrated field unit yet? Is that available for sale? If not, when do you anticipate that customers could sample or evaluate your product?
Wonderful question. I hope my CEO and my team is on the line and hear that. I cannot promise you because I'm not a salesman. So I can tell you, if you give us the high priority, that's the worst cup of food. If you give me the commitment and if you tell me this is very useful, because I'm not telling you be bogus, I'm telling you everything is real, okay? But convert this into from the prototype into a real product. There's two stages. One stage is a field trial. We are very much anticipated for that, and we are very much prepared for that if there is a need. So this is one stage for the field trial. The field trial, we can learn. We both can learn. The customer can learn, we can learn. So we group all the questions and issues together. Then the next stage is a final product. And of course, this will take some time. I cannot promise you this. This it's an entanglement issue. It's how the customer and how this organization, FOSA, see if this is important. And if it's yes, then we can put all the effort into that, and we can develop that for this industry.
Okay, so it sounds like you're interested in hearing from potential customers who may want to investigate your technology and test it out, but you don't have a timeline yet. So I think probably the best course of action, if anybody's interested, is to just contact David or send an email to us, and we can put you in touch with David for those types of queries. Would that work for you, David?
Yeah, Mike, thank you so much, because I don't give you bogus response, because I would say, let's say the shortest time, maybe 6 months, we can, because it's already a prototype. If you don't give me so many stringent, extremely hard requirement, and we can quickly convert into a prototype, deployable prototype, and convert into a product. But if you give me add on to lots of new functions and features, and still requires a low cost, then my hands very tight. Okay, so
sure, yeah. So
Yeah.
another question. Can you describe whether or how machine learning and artificial intelligence are envisioned for use with your new technology? Is it part of the solution today, or is this something that will be added in the future?
It will give the potential to be added onto the future, because I can tell you this, based on to our expertise, we are mostly on hardware and a very detailed intricacy of the mechanics and also optics. Software part is different. We just want to make sure the software AI, the integration is something like a very good restaurant, a chef. We can provide all the beef and the onions, all those kind of things to you guys, and you can make a very nice plate, and then you can entertain all the industry and all entertain your restaurant, and you have lots of customers. In other words, all the data we feed to the future network management system, which is the AI, it will have the basic raw data, required raw data. And that means, for example, the fiber. The fiber, you see the fiber and you use the triplets detect that, and you know the temperature variation at different regions, the seismic waves, and the traffic patterns, all those kind of things. you can record it into data. The more data you have, the more leverage you have for the AI, do the calculation and do the simulation, and you will know your region. Let's say Chicago region, or maybe Dallas region, or Los Angeles region. Maybe the fiber deployed is very different. So if you know all those information, and just give you a simple example, when I work in Verizon, a new fiber put underground, spend tons of money, and the next few days get a cut. So you know, if that is the case, you know which area is more risky rather than certain areas more safe. So all those patterns at this moment is purely by people say, oh, I have experience, he has experience, she has experience, and we have some data. But those data are sporadic and also scattered all around. With this echoes plus the triplets and maybe even quadruplets and quintuplets in together into the future, you have everything lifted up, found the buried ground, lifted into the network management system, and this information feeds to the cloud on the ground with anything you want to know. So yes, we will feed you the data. We're not planning to do our AI ourselves. It's a different job type. We're not really good at it.
Sure, I think that's very clear. Thank you for that. So looking at the clock, I think we've exhausted most of the questions, so we should probably wrap up the webinar. So David, thank you very much for your time and an enlightening discussion around novel applications of sensing and telecom and data center and so forth. We're looking forward to seeing your progress in the coming months and years, and we look forward to hearing more about that. Looking ahead from a FOSA standpoint, on May 30th at 11 a.m. Eastern Time, FOSA's Technology Outreach Committee will be hosting and presenting what's the killer app for large-scale fiber sensing deployments. So I encourage all who are attending today to look for an email announcing that, and to, if you don't get the email, just simply go to the FOSA website under events and webinars, and you can register for that webinar as well. With that, we conclude today's FOSA webinar, and thank you all very much for your attention and interest. And David, thank you for your time.
Thank you, Mike. Thank you, Joy, and thank you for the opportunity.